Good morning. If you're seeing this, it's because you weren't able to make the live stream this morning, and that's okay. So I'm going to go ahead and do it for you guys here. It just won't be as interactive.
So we're going to start by talking about electric fields. I'm going to start this presentation. So recall, before the break began, we learned about electric fields. We did our notes, we did our labs, but I'm going to go ahead and review it anyways, just so we have a good starting place. So an electric field is a property of the space around a charged object that exerts forces on other charged objects. So questions that we answered together in the live session were, what is an electric field? Students answered how charge, electric field, and forces are related, and then finally we kind of reviewed very simple examples of how to represent electric fields in diagrams. One thing I want to say, for the new information, we were going to originally learn Millikan's oil drop experiment as well as electric fields near conductors and capacitors. However, since this is our first time kind of doing the interactive stream and doing online homework, I decided to just go ahead and just do the oil drop experiment. So, what is an electric field? So if you go back to the first slide, I defined it as a property of space around a charged object that exerts forces on other charged objects. And this is really just the textbook definition for an electric field. We can represent this mathematically. And let me change this to color other than red. So we could say, well, the electric field, and let me change my laptop to 1 second. Okay, so the electric field is equal to the force of a charge divided by the unit charge, right? So we say the force of charge per unit charge. So we want to know how much does the electric field, right? How much does a source charge impact a test charge? And that's what the electric field is. And we can also draw that. I guess I could do it like this. So we can draw this, and we could say, well, here is our large source charge, and it has all kinds of awesome charge force. And here's our little tiny test charge, and it has a very minuscule charge force. And we do this for a reason, because we don't want to put a test charge in the field because that will change how the field interacts. We want to just see the field from this source charge. And we always assume that the test charge is positive, and we're going to go ahead and make this negative. And so this source charge, right, would attract the test charge towards it. And so really, the electric field, we could say, as all of this space in between here, the tendency of any charged object, if it were placed in these positions, would be to move along this line. And because the electric field, right, it has a hat, so we say it's going places, these fields show magnitude, and direction. So we put the test charge near a source charge, and it's going to move towards this negative source charge, right? And the tendency of the object to do that, we call that the electric field. So the larger the source charge, then the more properties that we have to deal with, right? So this becomes less simple. And we could even think, well, the force of the charge is Coulomb's constant, right, times Q1 times Q2 divided by the distance squared. So we can kind of relate Coulomb's law to electric fields as well. And so electric fields act on an object, right? You could think of them, if you were standing here, someone's pushing you towards it. It acts on the object without touching it, though. So we have this invisible someone invisibly pushing. So it's not like they're actually pushing. So we call that a field force. And a field force is a force that acts on an object without touching the object. This isn't the first time we've learned about field forces. Another example of field forces that we talked about earlier was the sun. So the sun has a lot of mass, right? So it has a large gravitational force. And let's say you're an astronaut in space, you're just floating along. Maybe you're tethered to a little spaceship. This sun, right, it's much more massive than you. This sun would pull you in towards it, right? And we know that objects might then rotate about it. And so this is the gravitational force. And the gravitational force is also a field force. And we could draw lines just like electric field lines. And that's kind of the property of the space between two massive objects, or maybe one big massive object and a tiny massive object. So this is the same thing. We have one big source charge, and one tiny source charge. Okay, and the live stream, and the students have the opportunity to ask questions. You can see their questions posted in the live stream version of the PowerPoint that I put in Google Classroom. One question that we got online from the Khan Academy, and it's linked in the speaker notes. Oh, let me do this in the speaker notes. And so if you're looking for maybe a different way to explain things, please don't be afraid to explore different explanations, different videos online, because maybe it will help you better understand. So the student said, what is the electric field exactly? If the electric field is the force on a charge and the strength of the electric field can be measured, is the electric field just how reactive it is when a charge is placed in it? And so I just don't like the word reactive, because when I think reactive, I'm thinking potassium and we throw it in water, right? That's reactive because it combusts. That's my little explosion. All right, boom. And that's not what they mean here. So this reaction, because remember, when a force acts, right? When a force acts on an object, it causes it to accelerate. It can cause it to change direction or speed. And it could do both. So we'll say and or speed. So that force causes it to change direction and or speed. And so in that sense, he's correct, right? The electric field really is the tendency of an object to cause another object to move when placed near it. So I would say you are correct. This is a great way to conceptualize an electric field. And what the person responded with was, this is a very hard question to answer in depth. But you have the idea generally right. If you put a charged object somewhere in space and you notice there's a force on it, that force is caused by the electric field at that location. The magnitude of the force is proportional to two things: the size of the charge and the intensity or magnitude of the electric field. Direction of the force is determined by the direction of the electric field vector. So basically, you're correct. You've got the idea down, and that's linked in the speaker notes. You can go ahead and examine other explanations for electric fields if you would like to. So how are charged electric field and forces on charged objects related? This is one that I had the students answer, but I'll go ahead and answer it. So the electric field, E, is equal, I'm going to do this in a different color, to the force on the charged objects, right? The F of Q divided by the unit charge. Divided by the unit charge. So you could think of these two as being inversely proportional. And then you could think of this as being directly proportional. But the bigger picture is that the electric field is the relationship between the charge and the force on charged objects, right? So the electric field is that relationship. So how are they all connected? By definition, the electric field is the connection between all of them. So the electric field is the relationship between the force on charged objects and the charge. And there are many different ways you could have your own answer. I really don't think there's a wrong way to relate these together. And finally, we reviewed how you represent electric fields in diagrams because you guys already have complicated diagrams in your notes. I'm just going to briefly remind you that we draw electric field lines. And here I've done two negatively charged particles. So electric field lines are diagrams of electric fields. We'll say diagrams of electric fields. Okay. So now we're going to learn some new information. Super exciting. So we'll discuss Millikan's oil drop experiment today. So in 1909, Robert Millikan and Harvey Fletcher performed an experiment called the oil drop experiment. To test whether charge exists in discrete amounts. And I'm not sure that they necessarily were trying to find a discrete amount on purpose, they just happened to do so. Because their goal was to find the charge of an electron, right? And if you can't have half an electron, then you're going to get discrete values. Again, I just want to remind you guys that we already know, we as a class, we already know the charge of an electron, right? We said E is the elementary charge. And it's 1.60 times 10 to the negative 19 coulombs. But at this time, all we'd known was that J.J. Thomson had discovered the electron. And that was it. So we were going to figure out, well, how big or how small is the charge on that electron? So what did we do? First, their apparatus looked more like this. I just couldn't make that in PowerPoint. And here they had a microscope so they could see the very small droplets. And you notice they had a circuit here. I'm going to go ahead and draw a little dial so they could change the voltage. That's my little, I don't know, alligator clip and wire. So they could change the voltage on their experiment. So they have two parallel charged plates. And remember, we talked about the convenience of having a parallel charged plate because then we get a uniform electric field. So we get a uniform electric field when we have two parallel plates. And this electric field is going to look like this. Just going to go from positive to negative very conveniently. So they had this device, their oil diffuser, and really their oil was here, but for my device I'm going to put my oil in a little spray bottle and they diffuse the oil. So they have all these little oil droplets that get sprayed in here, and then these oil droplets start falling because gravity. And then eventually you get some oil droplets in the electric field. Okay. So we know because we're on Earth, this oil droplet always experiences the force of gravity. But when it's in the electric field, it also experiences the force due to a charge. So this means it has an upward force and it has a downward force. Okay. So when these forces are the same, then the oil drop will be suspended. This means it's just floating in midair. I'll write that. We're just floating in air. And this tells you, because the force of the charge is in the upward direction and the force of the gravity is in the negative direction, if it's just floating and staying in one spot, those forces must cancel out, right? We would say the sum of the forces equals 0. So that I could say the force of gravity equals the force of the charge. And really, we know that the force of gravity is just mass times gravity. We call that weight. So we could say the weight of the charged object is now the force of the charge on that object. Okay. So Robert Millikan and Harvey Fletcher, they repeated this experiment numerous times. So they were getting several measurements of different charges. So we'll say they had several measurements of different charges. So maybe the first time they got 160, and then perhaps the next time they got 480, maybe they got 320, maybe they got 160 times 20, maybe they got 3,200 when they measured the charge on a drop. So they had all of these numbers, and what they realized is that all of these numbers, they were all divisible by 160. And in reality, it was probably like 0.00000000000000160, right? Because it's 1.6 times 10 to the negative 19th. But I wrote 160 just for convenience. And so they realized this is the smallest number we can get. This is the elementary charge. This is the charge of an electron. So this is the oil drop experiment, which they did in 1909 to find the charge of an electron. Okay, so finally we're going to do an example of the math that they did in their experiment. And the question is in the speaker notes of this section, so I'm just going to go ahead and read it out loud. So in a Millikan oil drop experiment, a particular drop weighs 2.4 times 10 to the negative 14 newtons. The parallel plates are separated by a distance of 1.2 centimeters. When the potential difference between the plates is 450 volts, the drop is suspended. What is the net charge on the oil drop? And if the upper plate is positive, how many excess electrons are on the oil drop? So you're going to start by writing what we know. We know that the weight, which is the force of gravity, is 2.4 times 10 to the negative 14 newtons. So just remember that weight is mass times gravity. So in some of the homework problems, I might have given you mass and not weight. And that the parallel plates are separated by a distance of 1.2 centimeters, have a voltage of 450 volts. So let's diagram what's happening. So they told you the upper plate is positive and your smaller plate is negative, and you have a charge suspended between the two plates. So if the charge is attracted to the positive, we know it's a negative charge. This is a negatively charged droplet. And so we have the force of the charge in the upwards direction, and we have the force of gravity in the downwards direction, and it's not moving. The distance between the two plates is 1.2 centimeters, and the voltage is 450 volts. Note that centimeters is not standard units. We need to convert this to standard units. We want this in meters. And I know in 1 meter, there are 100 centimeters. So I would move this decimal over 2 places and I'd get 0.012 meters. Okay. Some equations that we can use when we're working these problems. One, note that force of gravity or weight is mass times gravity. The thing that we love so much about parallel plates is that we can say that the voltage is equal to the electric field times the distance between the two parallel plates. I guess you could throw in Coulomb's law, but we're not going to be using it for these problems. And then finally, know that the electric field is the force of the charge divided by the charge. So let's find the charge of this drop that's suspended. So I can say that the force of gravity equals the force of the charge. And here I see, well, the force of the charge is E times Q, but I don't have E, I have V and D. So here I see that E equals V divided by D. So now F of Q equals E, which we said is V divided by D. So V divided by D times the charge Q. And they already gave us Fg, so we don't need to put the equation in. I could just say 2.4 E negative 14 newtons. Okay, so that equals 450 volts divided by 0.012 meters. I want to get charge by itself, so I'd have 2.4 times 10 to the negative 14 newtons times 0.012 meters divided by 450 volts. And when I do that, I get, let's see, 2.4 times 10 to the negative 14. Please remember, you can just press second, comma on the calculator to get the E, times 0.012 divided by 450. And I got 6.4 E negative 19 coulombs for the charge. And then I want to know how many excess electrons are on this charge. And so one electron has a charge of 1.6 times 10 to the negative 19 coulombs. So the number of electrons is going to be 6.4 times 10 to the negative 19 coulombs divided by 1.6 times 10 to the negative 19 coulombs. And so put that in the calculator. And I get that the number of electrons is 4. So there are 4 excess electrons on this drop that's suspended, and these 4 excess electrons have a charge of 6.4 times 10 to the negative 19 coulombs.
All right, so your homework 7, the oil drop experiment. It's just 4 problems, and you have 3 different ways that you could turn it in. One way you can do it is in Google Forms. Please make sure that you answer all parts of the questions, not just the first part of the question. And I will have to grade your answer. The computer cannot grade it for you. Another way you can do it is the Google Slides. You should be able to edit it. Each student gets their own copy, and then you could insert, line, scribble. You can write all over the Google Slides. You could insert information if you want, text box, and type out your variables and make your diagrams. So if this is convenient for you, go for it. And then finally, if you don't like doing your homework online, that's okay. You can do it on paper. Just make sure you take a picture of it and attach that in Google Classroom so that I can see it, or scan it to me. So this is your homework for tonight. It's due on Tuesday though, so you guys have quite a few days to get this taken care of and hopefully work through any problems that we have. So this is it for me today, guys. I hope that you all really get the opportunity to learn from this video. I hope that you're all being safe. Thank you so much for working with us during this time. I know it's difficult and I know it's different, but you're all being amazing. We only have 3 more weeks. Let me know if you have any questions. You all know how to contact me in Google Classroom or through email. Thank you so much and goodbye.